So welcome to another session of Everyday Mathematics. Here at Everyday Mathematics, as we always say, we do enjoy solving the harder problems, but above all, we also see and appreciate the beauty in the simpler problem. So today's problem comes from the MIT 2024 Integration B Finals, tiebreaker number 4, which is the in the definite integral from x equals to negative infinity to positive infinity of sine squared of 2 to the power x cosine squared the power 3 to the power x times into brackets 4 cosine squared 2 to the power x, another bracket 4 cosine squared 3 to the power x minus 3 close bracket squared minus 1 close bracket. So this is quite an intricate problem. I hope you do stick around, see how we propose to solve it. But before I jump into solving it, I'd like to shout out to our subscribers. Thank you so much for the support. We don't take that support for granted. It's because of your support that we come in, day out, to try and share with you some of the solutions that we think befit these problems. For our first-time visitors, we'd like just to inform you that here at Everyday Mathematics, what we do is we go around and about and look for problems that seem hard, and then we come back with some solutions that we propose to be apt to some of these problems. To our repeating visitors who haven't gotten the motivation to subscribe, we really would like to beseech you to consider subscribing to our channel. Your support will go a long way in giving us the extra visibility that we need. So this problem is, as I said, quite intricate. The first thing that I would personally do is I look at the innermost bracket, and there we have a combination of 4 cosine squared 3 to the power x minus 3. What is interesting here is we could play around with that. And then, so if we multiply cosine of 3 to the power x um, into this denominator, and then obviously have a denominator of cosine 3 to the power x as follows. You realize that we have 4 cosine cube 3 to the power x minus 3 cosine 3 to the power x over cosine 3 to the power x, because we multiply both the numerator and the denominator by cosine 3 to the power x. So the numerator here, for those of you who know the expansion of cosine 3x, it gives us, and here x is essentially 3 to the power x. So what that means is that in the numerator, we do have, in place of 4 cosine cubed 3 to the power x minus 3 cosine 3 to the power x, we have cosine 3 times 3 to the power x. And then in the denominator, we still have the cosine 3 to the power x. Now let's shift our focus now to the green part. That green portion can also be expressed by multiplying the denominator by sine squared to the power 2x. If we do that, here we've just opened up the bracket by squaring both the numerator and denominator. But if we multiply the green part both to the numerator and denominator with with sine squared 2 to the power x, what that essentially becomes is we have the square of sine 2 times 2 to the power 2x, right? So we've made the numerator that, since sine 2x is 2 sine x cosine x. So when you square that, that becomes 4. And so that's 4 sine x cosine x. And that's the same thing that we've done with x being 2 to the power x in that regard. So What that means is now we can keep the denominator as it is, and the numerator can now be simplified as sine 2 times 2 to the power x, all that squared. Okay. And the denominator obviously just remains like that. But as you can see, this and this can cancel with this when you multiply with whatever is outside the bracket. And then you're left with the numerator only when we multiply by this component that is outside the bracket. So that now leads to, we have now the integral from x equals to negative infinity to positive infinity of sine squared 2 times 2x times cosine squared 3 times 3x minus, because we have this 1 here, this entire thing remains. So you're minus sine squared 2x times cosine squared 3x. So we can simplify this further. Since the bases here are the same, we have sine squared 2 to the power x plus 1 times cosine squared 3x plus to the power 3, the cosine squared 3 to the power x plus 1 minus sine squared 2x times cosine squared 3x. If you look at these two functions, they're pretty similar, only that in the first component here, or the first term, x has been replaced with x plus 1. So if we say if fx is the same as sine squared 2 to the power x times cosine squared 3 to the power x, then what we can see is that our integral here, which is the same as that complicated integral we're given at the beginning, is the same as the integral from x equals to negative infinity to positive infinity of f of x plus 1 minus of fx, since this is fx, right? Now, one interesting thing is with this integral, when x tends to negative infinity, 2 to the power x tends to 0, 3 to the power x tends to 0, 2 to the power x, and so on tends to 0. So this entire thing just collapses to 0. And that is a very, very important thing to, first of all, have in mind. So when x tends to negative infinity, 2 to the power x tends to 0, and also 3 to the power x tends to 0, right? So fx being equal to sine squared 2 to the power x cosine squared 2 3 to the power x tends to 0, since sine squared 0 is just 0. So this tends to 0. And also, let's continue. So what that means is that I here, being the integral of this, can be considered to be the integral from x equals to infinity to x equals to positive infinity of fx plus 1 minus fx. And then the integral from x equals to infinity to x equals to a is equals to the separate integral of this fx plus 1 from negative infinity to a minus the integral of fx from x equals to infinity to a. Since we know at negative infinity, or as x tends negative infinity, these integrals tend to 0. And what that means is that the integral IA, which is the integral from x equals to infinity to positive to a, becomes the integral of fx plus 1 minus the integral of fx. And if we let x prime be equal to x plus 1, then the x prime is the same as dx, meaning that we can insert x prime in place of x plus 1, but with the limits, the lower limit still remains negative infinity. The upper limit becomes a plus 1. So this integral here still becomes, we can just replace everything back with x. So the integral of fx plus 1 is the same as the integral of fx from negative infinity to a plus 1. And what that means is that we can now expand this such that we have the integral from infinity, negative infinity to a plus the integral from a to a plus 1 minus this component that is still there. So you realize that this and that can cancel out, and our integral IA remains the integral from a to a plus 1 of fx. But notice our original integral is the limit of a tending to infinity of IA. I being equal to the integral from x equals negative infinity to positive infinity of fx plus 1 plus minus fx is the same as the limit of a tending to infinity of the integral from x equals to negative infinity to a of x plus 1 minus fx. But we've now realized that this IA is the same as the integral of fx plus from x equals to infinity, a to a plus 1, with a tending to infinity, therefore, meaning that this expression is the same as our original expression, I. Now, we know what fx is. Fx is sine squared to the power x times cosine squared 3 to the power x. We can express that into a double angle formalism by removing the squared. So sine squared 2 to the power x is the same as 1 minus cosine. 2 times 2 to the power x over 2. Cosine squared 3 to the power x is the same as cosine 2 to the power x plus 1 over 2. Now, when you multiply that, we get a quarter times cosine 2 to the power 2 times 3 to the power x plus 1 minus cosine 2 times 2 to the power x times cosine 2 times 3 to the power x minus cosine 2 times 2 to the power x. And we can isolate this 1 here and then play around with these terms, the extra terms we've gotten. But you realize that with this constant here of 1, when you integrate that, you get x, and then applying the limits appropriately, we are left with just a quarter times 1. But the important thing here is that as a tends to infinity, these other remaining terms, we have the lower limit being positive infinity and the upper limit being positive infinity, right? So this a quarter plus a quarter, the integral from infinity to infinity of this cosine terms here implies that this entire thing just tends to 0 because there is no interval. The interval is limited to infinity. And so this entire terms here tend to 0, the entire integral. And so our answer remains to be a quarter. And that is the answer for this very intricate problem. If you look at the plot of this problem, it's really very, very complicated. But I think it just did require you to exploit the cyclic or the relationship between fx plus 1 and fx. Thank you so much for your attention. Until next time, Matuta Luka Lapo Shenfua. If you've not subscribed to our channel, please consider subscribing to the channel. Thank you.